Hello, everyone, and welcome back to the Hyperthesis. We are at the episode 8 now, and today we're going to be discussing more things on climate change. But first, my name is Pheely,
My name is Patrick.
And I'm Liam.
and yes, as I mentioned today, our main topic is going to be on climate change and how we view it as scientists and also physicists. And to start that, let's start with Patrick. Actually, I forgot this section. Anything new and interesting in the past week?
Uh, well, for those of you who haven't heard, CERN started up again, or specifically the Large Hadron Collider. So CERN, or the European Nuclear Research Council, uh, to anglicize it, runs the Large Hadron Collider, which is a 27-kilometer circumference superparticle collider in Geneva. And it was down for a couple of years while they were making upgrades to it, and they finally turned it on again, and it got up to 13.6 tera electron volts, whatever that means. But essentially, these are energies that particles are traveling at inside the detector, and within the detector, they're smashing together, and so the energy is higher than it's ever been before.
Yeah, I actually didn't know they were off. I thought they were on this entire time because I think the data, they had so much data that I think when last time they turned it on, that I thought it was a continuous thing that already always have new data. But apparently the new data was the old data that hasn't been processed. And the second thing is, well, the mega electron volt is the unit of energy. But if people remember the famous Einstein, not quote unquote equation, because Einstein equation means different thing to a lot of physicists. Well, his famous equation E equal mc square, if the particle is moving, it has a term that has to do with speed in it in front of mc square, which is the gamma mc square. And that's encoded speed, so you can actually basically convert energy to the speed of particles that's going very fast, so very close to speed of light.
Yeah, so these particles are going like 99.9999, many nines percent the speed of light. So they're going really, really fast. And so their speed is determined, or it's converted to their energy. And so when you have one beam of charged particles moving around quite quickly, and then another beam going in the opposite direction, they're both moving around at, I think it's like 7.8 tera electron volts of energy or of speed. And so when you meet them in the middle, then those two energies combine to 13.6 tera electron volts, or 13.6 trillion electron volts.
What was the previous energies they could get to before they shut it off for a while?
I believe it was around 13 tera electron volts. So
Okay.
they went up by about 600 billion electron volts in energy.
Yeah, I think as scientists, we are so familiar with using mega, giga, tera, right? And when you talk to other peoples, you kind of have to translate to like billions, trillions, and to me, it's kind of weird because like it makes more sense to use like basically scientific notation or like, oh yeah, 10 to the power of 9 makes so much sense. But like I'm still not used to the concept of using billions and trillions. I have to actually think and convert back to the scientific notation.
Yeah, it's kind of handy that computers are getting better because we're starting to get terabyte, and we've had gigabyte drives for a while. And so people who are even somewhat familiar with computers kind of has an idea of what like mega and giga and tera is, and eventually peta. So I I'm guessing that there's more of an intuition for these sizes now that these larger file sizes and drive sizes have become more popular. But yeah, it is challenging to convert it to different words.
Yeah, I still struggle to convert it to words in my head. And I guess people are becoming more familiar with the bigger numbers, but maybe not as familiar with the smaller ones, at least in that context.
Well, back to the CERN stuff. Well, I think what they're trying to find now is that those exotic matter, right? The one that, well, you think of proton, neutrons that make nucleus, they're made of three quarks, and that's really common. And if I think if four or more quarks make up a particle, I think five, the pentaquarks, they may be just they're trying to actually find, because these type of exotic matters don't usually exist in basically standard conditions. So they have to have this very high energy, and they don't last that long, fractions and fractions of a second.
Yeah, so the Large Hadron Collider, since it's such high energy, is really useful for finding very rare events that probably haven't been seen unless you're in like exploding stars or black holes or at the beginning of the universe when it was very hot and there was a lot of energy in a very small space. So trying to find these different configurations of quarks. So you mentioned that protons and neutrons, which make up atoms, are composed of three quarks. We also commonly have longer lived two quark arrangements. So if you've ever heard of cosmic rays coming down, some of those can be two quark particles like mesons. But in this case, they just recently announced that they found new types of penta and tetraquarks. So 4 and 5 arrangements of quarks. And this is known as exotic matter, and they're because it's not some sort of new particle that we're finding, but new combinations of particles. And these live for a very short time, but it's still interesting to see just what happens in that very high energy soup that's produced with these collisions.
Yeah, so I get that they're making, or they're increasing their energies to see what kind of particles they can make, and then that tells you, is your model of physics, is it correct? Is it bad? Does it need modification? But would these, like pentaquark or whatever, would they ever appear somewhere in nature? Or maybe during like the Big Bang or something? I don't know.
I mean, the theories say that yes, they were most likely a lot more common right after the Big Bang because of all of the energy that was present there. So the temperature was a lot higher during the first couple milliseconds to seconds to even years after the Big Bang. And that large amount of heat allowed for these particles to actually exist because I think we discussed this in a previous episode. Heat is just the movement of particles. And so if it's higher heat, you get a lot more movement and faster movement of particles. And so when you have, say, a proton and a proton colliding at the beginning of the universe, then they're more likely to form these types of things.
Well, I wonder if these tetraquark and pentaquarks violate any existing theories in standard model, because I don't know if I ever in class or in readings like had to read about pentaquarks, right? It's kind of strange. Are those any conservation laws that are violated?
So far as we know, no, there's nothing that's been violated. In fact, a lot of these tetraquarks and pentaquarks were first predicted when the theories behind quark interactions and quarks themselves became pretty commonplace. So before we knew what composed the parts of protons and neutrons, we wouldn't have thought these types of quark arrangements possible. But with the introduction of quarks and all the theories behind them, these are actually well predicted and don't really violate anything. But the Large Hadron Collider, it's not just searching for these types of exotic matter, so different types of quark arrangements, but it's also searching for new types of particles.
Well, I feel like these exotic particles, even though they are possible, but they don't last very long. They're very, very short life. So if we keep adding quarks into the particle, at which point is there a threshold of like the shortest lifetime that we're gonna say there's not really a particle anymore? They're just like they're just there for not long enough to be considered a particle. If it's there that very, very short time, is it even a particle?
Well, Yeah, so if you're talking about the Big Bang, a lot of the interesting stuff happened, like Patrick said, in kind of milliseconds or even less. So maybe these very, very short lifetime particles, like they mattered a lot then. Maybe their time scales are too small for us to really care now, but maybe during the Big Bang they were important. I'm not sure.
Plus, who knows how time moved differently in the Big Bang? So something that's super short lived, so on the order of like I 10 to the negative 22 seconds, whatever that prefix is, something that was short lived now may have been longer lived back then due to relativity or even just time being different and going at different scales. But just going back to your point about can it be still considered a particle? Absolutely. If there's evidence that that particle existed, then that is still a particle. So some of the particles that we've found are force carriers. So for those of you that have heard of the strong force, the weak force, even the electromagnetic force, some of those interactions, if you've ever seen Feynman diagrams, there's usually some sort of force carrier. So a particle that represents that force and carries the effects of that force. So for electromagnetism, it's the photons. So it's photons that carry the electromagnetic force. So the light that you see is the same force carrier for anything that's electromagnetic, even if you can't see it always. Whereas these other forces, like the strong force and the weak force, have very short lived force carriers, but they still definitely do something and they still exist. And also the Higgs boson is another, not quite a force carrier, but it's short lived, but it definitely is significant.
Nice. So CERN, I think can expect a lot more in the next 5 to 10 years. What's gonna happen with the particle accelerator, and a lot to work on in terms of data because those are very, 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 very large data set.
Yeah, there's a lot of data coming out, many petabytes of data. And just a quick note on the future of CERN. So they are trying to plan for 100-kilometer circumference ring. So the current one is 27 kilometers. So 100 kilometers, they'll be able to get up to higher energies. And I just want to mention the scale of these energies. So we're saying 13.6 tera electron volts. But fun fact is if you clap your hand and make a noise, that's far more energy than is being produced in one of these collisions. So there's a lot of energy going on, but the energies are actually quite small compared to what we deal with on everyday scales.
Well, but you condense that into one particle, right? We have like trillions, I don't know, more than trillions, like 10 to the 23 particle in like 1 gram. You think of Avogadro number, right? There's so many particles. So, and also this concept of like energy and heat, or heat can be, kind of like the mean field theory kind of thing. So it's kind of averages. Nevertheless, that's the interesting topic, the very interesting topic that happened in the past week or so. So now we're gonna move on to our main topic, which Patrick will be the most expert in this room, in this chat that we have. Anyway, Patrick, want to take it away?
Yeah. So as Pheely mentioned at the beginning of the episode, climate change. It's pretty important in the modern day. And it's one of the reasons why I switched fields from physics into environmental sciences, because it's an issue. It's a big issue. And so I thought it would be nice to do an episode just kind of introducing the topic, explaining the evidence behind climate change, and just discussing it, viewing it how people from different sciences view it. So, of course, Liam and Pheely are physicists, and I'm an environmental scientist currently, still new to the topic, but we're going to try our best to look at it from different perspectives and how climate change makes sense that it's happening and what causes it in the first place.
Well, I did take a course of like introductory course in earth science to learn about tectonics and climate change. Not really specifically climate change, but it was definitely mentioned. And one of the main thing that was discussed was that we know that Earth has been through many climates, right? We have been through ice age. We have been through when it's very hot, like very volcanic, and climates always change. And the point that was made in that class was that, well, it always changed. So why do we care? Apparently, the rate of change matter. So now the rate that it change is unprecedented. It's definitely caused by humans. I mean, it's easy to see that it would change. I mean, we release these gases, into the atmosphere so much from industry, from agriculture, everything concentrated onto atmosphere. Even there was what's this that gas, the CFC, chlorofluorocarbon, that was banned. Yeah, that was banned because it actually destroyed the ozone layer. But before that, we didn't know. We just released so much of it. It was used to be in all the spray cans because I think it was part of their manufacturing. So we had to put those gas in to put pressure on and such. And we have been destroying our climates for quite a while. And also to note is that those climates that I mentioned, they're not very suitable for living. We're in this very special time where the climate is perfect for, well, not super perfect, but they're nice enough that human can live quite comfortably.
Yeah, so there's certainly a lot of factors affecting climate change now and leading to the point where it's starting to become uncomfortable and unconducive to human life. But you're absolutely right. There are many different evidences that point to natural climate changes. So ever since the Earth cooled several billion years ago, the climate has been in flux, and it's constant flux, but it's also very slow flux. So we know that around the time when the dinosaurs were living, it was pretty much tropical everywhere. It was a lot warmer. We also had a single giant continent known as Pangaea, or Pangaea, depending on who you're talking to. And so we know that at one point it was quite warm, and then it cooled off, and we're still coming out of that stage of cooling. It may have cooled off a couple times since then. I'm no geologist, so I couldn't tell you exactly what we know from the rock record. But there are definitely periods of warming and cooling that depend on a lot of different factors. So there are natural cycles for the amount of carbon dioxide in the atmosphere. I'm sure the introduction of trees had a very significant impact many hundreds of millions of years ago on the amount of carbon dioxide within the atmosphere. And there's also fluctuations within the Earth's orbit around the sun and the different ways in which the moon and the sun pull at Earth and how the Earth actually wobbles as it spins around.
Well, if or when the human dies off, I'm sure the Earth can regulate itself, right? Because in this grand scheme of thing, these change in temperature, it's not that much. It's like small part of the cycle. What's different, what should matter is that in the next 50 years or even less, we might not be able to live if it's going into on with this rate.
Yeah, the Earth has definitely survived some mass extinction events, some as much as 99% of the species being wiped out. I forget who said it, but it may have been Bill Nye. And it was, the Earth can survive. It's us humans that we need to worry about, to paraphrase. But yeah, it's absolutely a human issue, not an Earth issue. The Earth will be fine in a couple thousand, tens of thousands of years, but humans might not be around to enjoy it when it gets back to normal.
Well, it's because to think about it, like the condition that facilitate life, that's actually what we are looking for in other planets, are where the planets are in the orbit relative to the star. So it doesn't matter that much what we do on this because the material and the elements are already there. If we just ruin it, it will regulate back because we are at the perfect orbit for life. And well, in a way, like to us, it's just the species if we're gonna survive, which is tough. If you look at the history, fossils and whatnot, a lot of them gone extinct. Even in our time, in our lifetime, we would see a bunch of species go extinct, and sometimes people are very upset about it, but it's actually a very natural way of life because some species are gonna die off, some new species gonna become more and more. But the thing is, back to the, my point of the rate of change is ridiculous how fast they are. Unless there's some catastrophic event, maybe all volcano erupts or something, which probably happened at some point that killed a lot of species. But now it's not natural; it's artificial.
Yeah, there's a really interesting graph. It was originally called the hockey stick, and it shows, I believe, global temperatures on average over the past couple hundred years. And it's a pretty straight line. There's some wobble in it, and then just shoots up, and that's within the past 100 years, if that. And it's called the hockey stick because it looks like a straight line and then a swoop like a hockey stick. But yeah, it's certainly a very different rate of change than what the world has ever seen from what we know. There definitely are volcanic eruptions that happen and other cataclysmic events that greatly affect the climate. But even something like a volcanic event, so Krakatoa exploding, led to a summer, or I think it was called a year without summer, because the effects of a volcano exploding actually blocks out sunlight. And that blocking of sunlight means less energy gets to the Earth's surface and it's cooler overall. So we are kind of doing the opposite of what volcanoes are doing or other natural events like that, where we're adding gases to the atmosphere and heating it up instead of adding gases that can help cool it down.
Yeah, when I think about volcanic eruption, it's such a, a grandeur, because like think of how much ash we have to put in the atmosphere for the entire city or the entire peninsula got covered. Like the sky got covered with ash, so much ash that the sun couldn't go through. I think of how much basically dust you have to put in the sky. It just, the scale is just crazy compared to a normal human like us. And to me, I want to see it, but I do not want to live in it. Yeah, other evidence I see is the pictures or photos of ice caps, polar caps that are receding at quite an alarming rate, and those are water. Like those, they are water, so they're gonna be melted into the ocean, and the sea level increase that we have seen in the past, actually even in the past few years, is alarming. Because some countries are actually below sea level. I think the Netherlands is below sea level. They have a wall around it, and if the sea level keep increasing, I think there was a website or some kind of map that let you see, if it goes at this rate, how many years, and in so many years, how much of part of the map would be submerged. If you think of the Atlantis, that the kind of mythical city, that might as well what happened, right? But a lot of cities would be underwater.
Yeah, it's interesting to think about and see the effects. So the sea level globally rises only like a few millimeters a year, but over time that definitely accumulates and is most likely accelerating. But it's also interesting to think about how much lower the sea level would have been, say 10,000 years ago at the tail end of the last ice age, because all that water that produced the glaciers and these giant ice fields in Antarctica and Greenland and even Canada would have originated most likely from the ocean, because that's where most of the water is. And so it's kind of interesting to think, again, these natural cycles where, everything was already flooded at one point, and then an ice age came, took away a fair chunk of that water, and now it's going back in. And I remember reading, I think it's if all of the ice caps melted, so Antarctica, Greenland, all the glaciers, I think the sea level would rise 60 or 70 meters, which is
Jeez.
a lot. Nova Scotia would probably be pretty submerged. Florida's gone. Amsterdam and the Netherlands also gone. So there's no, it's not as likely to happen within our lifetime. And depending on what we can do with climate change in the future, it might not happen at all. But if Antarctica melts, then, well, we are not sitting pretty.
Yeah, it's kind of depressing. There's this thing, it's like the World Doomsday Clock or whatever it's called, and it tells you like on the scale of the Earth or the time scale of like the existence of the Earth or something like that, how much time we're predicted to have left, and it scales it down to kind of like an analog clock. And yeah, it's pretty. It's if starting at 12 is kind of the beginning of Earth's history, or maybe it's humanity's history, I don't really know, but we're like half a minute away from doomsday at all times.
Yeah, a lot of other prominent species lived longer than a few 10,000 years, right? So even with all technologies, and if you imagine being able to not be able to outlive dinosaurs, who they just literally live their life with no technology, and we just ruin ourselves by just having technology and such. And to me, it's kind of it's kind of sad, and also like we kind of have to blame ourselves. I mean, if you can't just beat going like without technologies.
Yeah, it's interesting to see what we've done, and it's especially interesting to see that essentially all boils down to one simple physics principle where some atoms and molecules absorb light differently and reflect it differently, which has led to this whole mess because of the different properties of atoms and molecules. So in the case of climate change, one of the big contributors, if not the biggest, or at least the one that we use to base all greenhouse measurements off of, is carbon dioxide. And because it interacts with infrared light in a certain way and reflects it back towards the Earth, instead of letting it pass through the atmosphere and out back into space, the energy that we receive from the sun is more likely to be trapped. And so if you have more of this carbon dioxide that's interacting with the light, then you have more light that's getting trapped in and a heating. And so it's a very simple principle, but it's leading to devastating results.
Like most organisms use oxygen and create carbon dioxide, including plants. If you put plants in your room without the sun, it actually create carbon dioxide, could actually poison you. But with photosynthesis that use carbon dioxide to create oxygen and energy and whatnot, that's why plants are so amazing about it. But I think there are people trying to make buildings that have the same function where it basically turn carbon dioxide into oxygen, but not as well, maybe more effective than plants, but not as much in terms of quantities.
Yeah, I was gonna say, like, plants kind of do the opposite. They take in CO2 and produce oxygen, I thought, right? Or at least that's what someone told me in high school, chemistry.
Well, yes, but that's the photosynthesis process, right? That does that. But plant has to breathe, right? It also has to take oxygen in and create out carbon dioxide still.
So couple cool things to think about is, one, all the carbon dioxide that we have now was most likely stored in plants or organisms. So the crazy amounts of carbon dioxide we're seeing in the atmosphere right now was once before in the atmosphere. And all these organisms are breathing and producing carbon dioxide, but also building molecules and other things from the food they ate. And not all the carbon went towards producing carbon dioxide. Some of it went to bodybuilding, but not like your Arnold Schwarzenegger bodybuilding, but like physically building bodies. And so that carbon that was breathed in, whether by plants in the process of photosynthesis, where it got trapped and bonded with other atoms to form, say, glucose or fructose or all of these different sugars, that was once in the atmosphere, and then that got buried. And now that's our fossil fuels, is the metamorphosized carbon chains that were produced from essentially plants. Now, the other cool thing about that is trees kind of suck at actually removing carbon from the atmosphere. And not that they are terrible things. I believe that there should be more trees, and that's why my research is focused on that. But algae and essentially bacteria and different aquatic organisms that are photosynthetic do a much better job at actually storing carbon and taking it out of the atmosphere.
Talking about carbon, if you think about life and stuff, on Earth, we are basically carbon-based organisms, right? Where most of the building blocks of life on Earth are carbons. But there are people who hypothesize that you go to some moons of Jupiter or Saturn. Don't remember quite well. It could be maybe the silicon-based life, or because they're very specific thing about carbon that's make it so special, because it can form a lot of bonds, and it's basically create this building block. But yeah, it's pretty interesting the way we use carbon in so many things. But one thing that I want to mention that growing up I heard a lot of is ozone. The ozone layer, you see holes in the ozone so the lights come in. And I think one of the property of the ozone layer is to basically block the UV, the ultraviolet, and you have UVA, B, C, right? And I think some more dangerous than the other. And I think the ozone layer actually mitigate those damages that would come down. And now, like the CFC or greenhouse gases actually puncture holes in those ozone layers, which are actually very evident.
So, what is ozone? I think if I remember, it was 3 oxygen molecules kind of bonded together, but it had this special type of bond, and I completely forget what it was.
But yeah, so it's interesting to talk about chlorofluorocarbons because of their effect and the response to them. So when I was still a physics student at our old university, I worked with a professor there who actually studied different fluorocarbons. So these are carbon chains with fluorine atoms on them, and the chlorofluorocarbons can also have chlorine on them. And it's actually the chlorine that causes the issue. So the chlorine, once it's high in the atmosphere, can break off from these molecular chains, and then it will go after these ozone O3 molecules. And so that's what breaks down the ozone layer. But it's also really interesting to learn how these fluorocarbons or these hydrofluorocarbons or whatever they are also extremely potent greenhouse gases. So in my research with Dr. Karine Labrie, we were investigating essentially the greenhouse factor. So how much light the different carbon chains absorbed and reflected light. And so from that, you can say, okay, this is so many times worse than carbon dioxide, for example. So not only were they bad for the ozone layer, they're also bad because they're a greenhouse gas. But the very interesting thing is we realized, hey, our ozone layer is getting destroyed, and it's being caused by these chlorofluorocarbons. And so it was a Montreal Protocol which was signed, which essentially banned the use of chlorofluorocarbons in refrigerants and in hairsprays and in all this stuff. And the ozone layer is being repaired now. It's slowly but surely being replaced with more ozone, and it's not getting destroyed anymore. So within the next couple decades, we'll actually see no hole in the ozone layer, which is just kind of shows the impact of good policy in having a positive effect for the climate.
Yeah, that's great to hear. And it's kind of like a show of how, science, it works sometimes.
Yeah, because I remember growing up when CFC was still used, and when it became basically global policy to ban CFC. Everybody have heard about it, and people didn't think much about it because you don't see it, you don't even feel it. and now that we can see some kind of effects that actually make it more personal to us, right? Like climate change feels out of reach. It's something that's global scale. What can one person do to climate change? We have 8 billion people. If one person can just change the whole thing, it would already have happened. But you got to remember that we have to be collective efforts, because these policies and stuff are basically an external force to this very complicated population that actually can drive a population into a certain way or certain configurations.
Yeah, it's definitely the will of the people, but nowadays it seems that people, to affect policy change, need to vote with their wallet, essentially. So an example of this is electric cars. So the technology has definitely gotten better, but electric cars 10 years ago, when a certain company first introduced their popular model for, I think it was close to $100,000 and up to $200,000, only really rich people could afford it, but people still bought them, and that allowed for that company to produce lower cost models, which honestly are becoming quite common now, at least in Edmonton. I don't know about in Ontario. And now all these other companies are coming out with electric cars as well. And that also led to more policy change. As the electric car became popular, politicians began to realize, oh, hey, this is actually something that is having an effect. Maybe we should do something about it. And so, for example, Canada, I think, will be banning electric cars by 2035 or 2040, along with many other countries.
Yeah, even on my trip today, I went to Ottawa, so I was on the highway for 5 or 6 hours. I saw many, many, many cars, 30 to 50 of them, from this other company. Sorry, from this specific company. Other companies are available. So yeah, it was good to see, like, electric vehicles they're becoming more and more and more popular slowly. But there's also, I always hear people make the argument that kind of the act of getting the materials you need to make these batteries is also quite destructive. I don't know if either of you can comment on that.
Well, I think, Patrick, you mentioned it well, I think you said banning electric car. I think you meant banning gasoline car. Yeah,
Yes.
but well, what I think should be more electric, actually, that can be more doable, is our public transit. Like buses can be electric, because the actually people who make electric buses back in my country, there are little electric buses they try to make, but people, it's just, well, there's a lot of things that have to happen. But if public transit became electric and become cheaper, I'm sure a lot of people would not need to buy cars. Because when I go up, like last week, I went up to the more northern Ontario. That's like, well, I asked my friend, how do people get anywhere? There are no buses. Like, well, you kind of have to have a car, or you have to walk or take a taxi. So to me, well, public transit should be everywhere, and they can make it cheap, because, I mean, if they can make it electric, right?
Yeah, that's a big problem. Like, even where I grew up, like, public transit wasn't really a thing. You get a license and then you have to have a car to do anything. Because even where I lived, I was a hour and 30-minute walk from a grocery store, unless you had a car, and then it was like 5 minutes. But North America, there's a good YouTube video on this. But North America is it's designed for cars, not for people.
Yeah, it's interesting seeing changes even within the past few years to transit. I know in Edmonton, there are now electric buses part of the fleet, and they're also expanding some of the rail transit in the city, and that's all electric as well. But again, that goes back to policy change and making sure public transit has funding. I know in Alberta, some of the funding was cut for different types of public transit initiatives. I'm sure with some financial impacts due to the pandemic that other budgets were cut because no one was using transit. So it's definitely tricky, but there certainly is a good path forward.
Yeah, well, Canada and also the US, North America are huge, like in terms of the area wise, and it's tough to go interstate and whatnot without a car. Or I mean, there's train, there's railway and stuff, but to actually get to one city to another, there are not that many options. Compared to look at Europe, you can travel cross country with trains, or well, or if to be more populated like Japan, where the transit system are common, and owning a car, you actually have to own actually a spot to park it, which is expensive. They make a policies like that, right?
Yeah, it's interesting to see how different places handle, say, cars, for example. So making it prohibitively expensive to own cars is a good thing. But moving back to our, I guess, original topic and talking about climate change in general, uh, there are many ways aside from just having electric cars or more transport that we can reduce our impact. So there are different methods to remove carbon from the atmosphere, which is pretty major because it's essentially carbon dioxide, along with other gases that are causing this issue. But these things that absorb carbon dioxide are known as carbon sinks. So, for example, trees are carbon sinks. So, if you have large swaths of forest, such as the Amazon or the boreal forest, they absorb a lot of carbon, and that carbon is stored in their trunks. We also have a very massive carbon sink on Earth, which is the ocean. So, as the ocean heats up, it's able to store more carbon because it's able to suck in that carbon and essentially convert it to carbonic acid. Now, carbonic acid is what's not healthy about that because it's causing ocean acidification, which is leading to coral reefs being absolutely destroyed. If you've seen pictures of the Great Barrier Reef recently, it's essentially turning white instead of the very colorful reef that we know it to be or knew it to be. And that's because of ocean acidification, which is caused by more carbon dioxide. So there are definitely knock-on effects with having carbon sinks, but there are other solutions.
Well, the carbonic acid actually is the acids that make pop fizzy. So maybe we could basically take carbonic acid out instead of putting in the ocean, putting it in our drinks. And well, it looks like we're running into the time. So before we get to the story, I'll get Patrick to take us to how to contact us and such, and also other comments he may have.
Yeah, so just to wrap up our conversation on climate change, there are some aspects of it that are natural, but humans are definitely having an effect. And it's really interesting to see studies about climate change because it's essentially a large scale experiment at this point. There's not much that scientists alone can do aside from produce results. So it's a very large scale scientific experiment, but only has a sample size of one because we only have one Earth. So it will be interesting to see what happens in the future. But yeah, moving on to how you can contact us. We are hosted on anchor.fm/hyperthesis. So you can find us there along with any of the other podcast applications that you may use, such as Google Podcast or Apple Podcast. We're also on Spotify. If you have any questions, you can either contact us on our Instagram at Hyperthesis Podcast, or you can send us an email which is hyperthesispodcast@gmail.com. So feel free to reach out to us, leave us a comment or a review on the Apple Store, which I think you can do. I think you can also do that on the Google Play Store. And feel free to give us a follow on Instagram, and you'll be updated when our next episodes are out.
All right. So today's story is in the essence of Liam's celebration of his birthday that came this past week. So I figured I would choose a story of a terror shed in astronomy and physics. Actually, I heard about this guy I was talking to my friend Waldo when I was visiting at his house. So this is the story of a Danish astronomer, Tycho Brahe. To me, if you're familiar with American literature, he's like the Hunter S. Thompsons of astronomy. So Tycho Brahe is a Danish astronomer. So he and his twin brother were born to one of Denmark's noble families in December of 1546. Unfortunately, his brother didn't live long and passed away early. And Brahe was actually raised by his wealthy uncle, who raised him until he was 18. So when he was just 13, he was sent by his uncle to study law at the University of Copenhagen. And I see this pattern of older scientists that were started when they're like 10 or 13. Apparently, this is common. So at the time, there are astronomers in Europe who predicted that year, when he was 13, there'll be a total solar eclipse on August 21st that year. So at the time, astronomy was somewhere between superstition and science. So they're not fully science. People still believe the sky as the heavens. And even though his uncle wishes for him to study law, he became fascinated with the heavens or astronomy. So he began purchasing astronomical instruments and read books on astronomy when they were available. And at the time, science hadn't changed much since the Greeks. So Aristotle, Ptolemy's Almagest, actually, when it was written in 150 AD, still used as a reference for astronomers, where to study where the stars are and how it works. I think it's Earth-centric universe and whatnot. So Tycho will make discoveries that actually change this gospel of astronomy that's kind of archaic. So he spent the decade in 1560 to 70 studying at University of Copenhagen in Denmark and also study in Germany. And along the way, he accumulated knowledge in mathematics, astronomy, and keep building his collection of scientific instruments. And the iconic thing about Brahe is this. So at the age of 20 in 1566, so there's an argument he had over some mathematical calculation, or some argue that was some astronomical prediction that escalated. So somebody told him he was wrong. He didn't accept it and basically said to the guy, you want to duel for it. So you want to use swords and duel for it. So it happened that he went on to this violent duel and he lost his nose, or most of his nose from the front up. So for the rest of his life, he actually wear prosthetics, which is metallic. It was rumored to be gold, but upon exhumation, we actually found that it was brass. It might be golden, it might be plated, who knows, but it was brass. So he has to live the rest of his life just from one argument in mathematics that's gonna get his nose cut off. Even though he got his nose cut off, he returned to Denmark in 1570 and built an observatory at the former monastery of Hervad Abbey, which actually was owned by his relatives. So it was at Hervad in 1572, 2 years after that Tycho Brahe made an observation in November that are not very usual, so very unusual observation. So he found that during a night sky there was a shining star / planet, a shining celestial body that's brighter than Venus. And that is strange, because what's more strange about that is appeared in the spot that no star had ever been recorded around the constellation of Cassiopeia. So upon further study, he realized that it's not just a new star, but it was a fixed star that was further away than the moon and all of the planets. So at the time he discovered this, or the climate and the intellectual climate at the time was that the heavens are immutable, they're fixed, they're unchanging. But he saw something, he observed something that changes. So in 1573, so a year after his observation, he recorded his findings in the book De Nova Stella, which translates to On the New Star, which he became famous for throughout Europe. So he actually established the term nova to describe a new star. But however, the star he particularly discovered was actually classified as a supernova. So I think that's part of the name come the supernova nova. All right, so this is very important because this new star that Brahe discovered upended everything that was assumed about the sky or the heavens, that they are immutable, because Aristotle believed so. So if the universe was not fixed and permanent, then anything is possible. So that actually changed the paradigm and how people think about it. So after that, he began lecturing on astronomy at his alma mater at University of Copenhagen and have a nice, impressive following across Europe. And one of the very interested people, very keen people in Brahe's work was King Frederick II of Denmark. So he was very impressed and he built an observatory for him on the island of Hven near Copenhagen, which was at the time one of the most prestigious observatory. Nevertheless, on this very same year he published his finding, he actually get married to the daughter of a peasant. So he was from a noble family. So at the time it was quite a scandal, which he also had 8 children with from the marriage. And he also have this string of scandals and such. So he has an entourage of eccentric figures around him to travel around and stuff. And he actually brought Italian artists to decorate his observatory. His observatory looks more like a castle than what you think of a building with a dome. No, it was like a castle decorated by Italian artists. So, and on his entourage has a jester, a dwarf named Jeb, who also allegedly has psychic powers. And he also had a pet elk that he fed with beer until it actually met its end after it got drunk and fell down the steps. There are a lot of crazy story. So Brahe actually fell out of royal favor after King Frederick II died, and the king's heir, the King Christian IV, actually didn't like the Brahes. It was speculated that the king's animosity actually comes from the rumor that Brahe had been having an affair with his mother, Queen Sophie. a rumor that also may have inspired Shakespeare's most famous tragedy, Hamlet. So after that, Brahe was forced to flee Denmark in 1597 and settle in Prague, so where he enjoyed the patronage of Emperor Rudolf II. So he found basically a new observatory and new supporter after the string of rumors and crazy stuff he has done. And as he was attending the banquet in his adopted city in 1601, he suddenly fell ill and died 11 days after at the age of 54 of kidneys condition. We will never know, maybe he was poisoned by his assistant, his team, or maybe the king himself.
Well, I mean, he fed his pet elk beer, so maybe he drank a lot. That's
Oh, that would go into liver mostly, but who knows? So Brahe's assistant was actually Johannes Kepler, as we know, is Kepler's law, a famous astronomer. So it was the thing that Brahe was possessive of the knowledge he recorded, not even allowing Kepler or his protege to access it. So there becomes a friction between the two. That's why people say, well, maybe Kepler killed him. We'll never know. So one of the most damning evidence after Brahe's death is that Kepler actually openly admitted to stealing his research, but later explaining that, I quote, "I quickly took advantage of the absence or lack of circumspection of the heirs by taking the observations under my care, or perhaps usurping them." And then Kepler would go on to develop his own theories on planetary motions and whatnot, which in turn laid the groundwork for modern astronomy and science for people like Isaac Newton. So this theory would not be possible without the research that Kepler had taken from Brahe, his own teacher, and the widely unknown yet very fascinating individual. So to end with Tycho Brahe, what a guy. Lost his nose in a duel, has a drunken elf and a jester, built the observatory as a castle, and changed the understanding as we know it of the heavens itself.
Yeah, I wish I could get enough NSERC funding to build a castle. That'd be pretty nice.
Yeah, and it also looks like we've opened a previously closed case about his murder. So maybe we'll get a historical investigator to look into how he died. But that is very fascinating to learn about Brahe. And with that, we will end the episode. So thank you, everyone, for joining us for, I believe, episode 8 of the Hyperthesis. And have a good day.
Take care.
See ya.